Hi guys, my name is Tensor. Welcome to part 2 of this Golang blockchain tutorial series. Today we're going to be looking at proof of work. We're going to talk about how we can implement the proof of algorithm in our blockchain, how it works, and the important concepts that make up this proof of algorithm. Before we do that, however, I want to refactor this code so that we have a module which contains all of the blockchain logic inside of it. So I'm just going to cut out all of this code here from the top where we define the blockchain down to the init blockchain function. Then I'll create a new folder called blockchain, and inside of it I'll create a file called block.go. And inside of block.go I'll define it as package blockchain, which is the name of the folder, and then I'll paste all the code in here and it will automatically get the imports as well. One more small thing that we do want to do is make the blocks field inside of the blockchain public. So we just make the B in blocks capital. This also means that anywhere else where blocks appears, we want to make that B capital as well. And of course, this is mainly in the add block function. Back inside of main, we can now import this blockchain module and then reference it inside of our main function. So here is the import, and I'm referencing it here when I'm calling the init blockchain function by calling it by its name blockchain. Now let's get into the proof of work algorithm. So inside of the blockchain module, we'll create another file called proof.go. And of course, this will be a part of the blockchain package. So we just want to give it the package of blockchain as well. This will make it so that we have access to any of the functions and structs inside of our block.go file, but we still get the organization of having multiple different files for our different ideas. Consensus algorithms or proof of algorithms are a little bit abstract to people who are new to blockchains, but once you understand why they exist, they're actually quite simple. The type of algorithm that we're going to implement in this particular blockchain is proof of work, but there are other types of proof of algorithms, for instance, proof of stake. Maybe at some point in the future I'll discuss what proof of stake is and how it works, but for now we'll just focus on proof of work. Now the idea is that we want to make it so that we can secure our blockchain by forcing the network to do work to add a block to the chain. This idea of work is essentially just computational power. So when you hear about miners mining Bitcoin, for instance, they're essentially doing this proof of work algorithm so that they can sign the blocks on the blockchain. And the reason why they get fees is because they're essentially powering the actual network by running the proof of work algorithm. And also by doing that, they make the actual blocks and the data inside of the blocks more secure. Proof of work also goes hand in hand with validation of this proof. That is to say, when a user does the work to sign a block, they then need to provide proof of this work. An important concept that goes hand in hand with this is the fact that the work must be hard to do, but that proving that work must be relatively easy. Alright, so now let's just write down the different steps for this proof of work algorithm that we're going to implement. The first step that this algorithm is going to take is to grab the data from the block. Then along with that data, we're going to create a counter or a nonce, which starts at 0 and increments upwards, theoretically infinitely. We then create a hash of the data plus the counter, and then we check the resulting hash to see if it meets a set of requirements. This is where the idea of difficulty comes in. If the hash meets the set of requirements, then we use that hash and we say that it signs the block. Otherwise, we go back and we create another hash and we repeat this process until we get a hash that does meet the set of requirements. Now the requirements that we want to meet is that the first few bytes of the hash must contain zeros. In the original Bitcoin proof of work specification, which is called hash cache, the original difficulty was to get 20 consecutive bits of the hash as zeros. This requirement gets adjusted over time, and that is essentially the difficulty. So the difficulty goes up, and that means that we must have more preceding zeros in front of the hash for it to be valid. Okay, so that's enough about the theory. Let's actually get into the code. I'm going to start out by taking an arbitrary value, 12, and assigning it to a constant called difficulty. In our implementation of this algorithm, our difficulty is going to stay static. If you are creating a real blockchain, generally you would have an algorithm that would slowly increment this difficulty over a large period of time. The main reason you want to do this is to account for the increasing number of miners on the network and also account for the increase in computation power of computers in general. Because we want to make the time to mine a block stay the same, and we also want to have the block rate stay the same. This means that you need to have a certain amount of computational power running the proof-of-work algorithm to produce blocks at that rate, but also keep the time to sign a block down. Let's now create our proof-of-work structure. This will contain a pointer to a block and then a target, which will be a big int pointer. Now this idea of a big int I'm not really going to go into. If you want to read more about it and more about how bytes work in general on computers, then I'll link some information in the description that you can check out. So the block is obviously the block inside of the blockchain, and the target is a number that represents the requirement that we described up here, which gets derived from our difficulty. Now let's create a function called newProof, which will allow us to take a pointer to a block and then produce a pointer to a proof of work. First, we'll create our target by casting the number 1 as a new big int. Then what we'll do is we'll take 256, which is the number of bytes inside of one of our hashes, and subtract the difficulty from it, and then we'll use the target to shift the number of bytes over by this number. So this LSH function is essentially, it's just shorthand for left shift. We can now take this target that has been left shifted and put it into an instance of the proof of work, as well as add the block to it and then return it from this function. So this is the first part of the algorithm. We're taking the block and we're pairing it with this target, and then we're going to take the block itself and create a new hash. If you remember, we're doing exactly that inside of this derive hash function, and we're going to actually replace this function with a function that we're going to create inside of the proof.go file. We'll call this method initData, and it will be on the proof of work struct. It'll take in the nonce, which is an integer, and then it'll output a slice of bytes. Like with the derive hash function, we'll grab the block's previous hash and the block's data, and then we'll combine it with another byte struct using the byte join function to create a cohesive set of bytes, which we can then return from this function. We also want to add in the nonce itself, because remember, we want to combine the data from the block with the counter, which is our nonce, and we also want to push the difficulty into this slice of bytes. To actually achieve this, let's create a quick little utility function which we'll call toHex. This will take in an integer 64 and output a slice of bytes. This toHex utility function will create a new bytes buffer, and then we'll use binary write to take our number and decode it into bytes. This binary big endian piece of the code signifies how we want our bytes to be organized, and then we can return the bytes portion of our buffer from this toHex function. So now back in our initData function, we can take our nonce, cast it into an int64, and then call toHex on it, and we can do the same for our difficulty constant. So thus far, we've taken the data from the block, we've created our counter or our nonce, and now we need to actually create the part that will create the hash from the counter plus the data, and then check to see if that hash meets a set of requirements. This main computational function will be called run, and we'll have it run on the proof of work. The function itself will output an integer and then a slice of bytes inside of a tuple, and it will take in nothing. In this function, we want to have what is virtually an infinite loop. So what we can do is define our nonce as 0, and then we can say for nonce less than math max int 64, and you can see this is a fairly large number. Inside of this loop, we want to prepare our data, then hash it into a SHA-256 format, then convert that hash into a big integer, and then compare that integer with our target big integer, which is inside of our proof of work structure. So first let's start by preparing the data. We can call pal init data with our nonce inside of it, and then we can take all of that data and hash it into a SHA-256 format using sum256. So that we can see this process happening, let's create a print statement which will print out that hash. So when we run this inside of our command line, we'll see the hashes changing until they finally find the appropriate hash, where it will eventually stop. Now let's convert our hash into a big integer. We define the big integer variable up here, so we can just say int hash set bytes and then pass in our hash. And now we want to compare our proof of work target with this new big int version of our hash. And if they compare and they come back with -1, then we want to break out of the loop, because it'll mean that our hash is actually less than the target that we're looking for, which means that we've actually signed the block. Otherwise, we want to take our nonce and increment it by 1 and then repeat the process again until this if statement actually comes back as true. Outside of the for loop, we can just call println so that we can have a little bit of space between our hashes, and then we can return the nonce and the hash from this function. So this is essentially our entire proof of work algorithm. Let's now modify our block so that we can store the nonce so that we can then implement the validation function. We'll store the nonce as an integer, and then we need to come down to create block where we're creating this block and put in 0 for our initial nonce. Also, because we're deriving our hash inside of our proof of work, let's just delete this derive hash function entirely. Now we can go ahead and modify the create block function so that it actually runs the proof of work algorithm on each block that we create. We can do this simply by creating our proof of work by passing in the block, and then executing the run function on that proof of work, which will return the nonce and the hash. We can then of course take the hash and the nonce, put them into our block structure, and then return the block from this function, and that will make it so that we can actually pass around this data properly. Now there is one more piece to this entire puzzle that we haven't covered yet, and that is the actual validation function. So let's now go back into our proof.go file, and we'll create this validate method which goes off of the proof of work and returns a boolean. The idea is that after we've run our proof of work run function, we'll have the nonce which will allow us to derive the hash which met the target that we wanted, and then we'll be able to simply run that cycle one more time to show that this hash is valid. So like with our run function, we set up our big int version of our hash. Then we can just call init data with our proof of work block nonce inside of it. Then we can take the data and convert it into a hash. And then we can convert that hash into a big int and put it into our int hash variable. And finally, we can run int hash computation on pal target and see if it equals -1 and just return it to see if the block itself is valid. So this fulfills what I mentioned before about the work portion of our algorithm being computationally expensive and the validation portion of our algorithm being relatively easy to do. What makes this proof of work algorithm very secure for a blockchain is this idea that if you want to change a block inside of the chain, you'll have to recalculate the hash itself, which takes a large amount of time, and then you'll have to recalculate every block after that block's hash as well to be able to say that this is valid data. So even though we can validate that a block is valid fairly quickly, the actual work needed to create the block or to sign the block is pretty difficult. And that protects the blockchain's data from being tampered by one single entity or even by a large amount of entities. Let's complete this application by adding our proof of work algorithm to our main.go file. We can do this fairly easily by adding 3 new lines to our for loop in here, which is iterating through each of our blocks. We can say proof of work equals blockchain new proof and pass in a block, and then we can print out the actual proof of work, and we convert the validation boolean into a string format, and then we can add a simple println statement to give us a bit of space between each of these printouts. Now let's go ahead and run our application. We only need to run main.go, and this will automatically build the blockchain module. You can see here that we have the work being done on each of our hashes, and each of our hashes has 3 preceding zeros in front of it. And then after the work is done, we then get the printout like we had before, except now we have the validation as well. We can see that all of these blocks are valid and that all the work was done to sign these blocks by simply looking at the validation value. Just to give you guys a good idea of how difficulty works, let's change our difficulty from 12 to 18 and rerun the blockchain. So here you can see I'm running the blockchain, and it's trying to find the hash that will sign the Genesis block. It has now found that hash, and now it's working on the first block. After roughly a minute, it found the first block's hash, and now it's working on the second block's hash. And after about 30 seconds, it found that hash, and now it's working on the final block's hash. And finally, it's finished. Now you may have noticed that for the second block, we have 5 zeros instead of 4. This doesn't mean that the hash is any less valid. This just means that it just so happens that another 0 attached to the front of this particular hash gives us a valid hash. Alright guys, well I hope this tutorial helped you understand proof of work. If you like this video, feel free to subscribe and like. If you have any questions or comments, feel free to leave them in the box below. And if you dislike this video, then by all means downvote it as much as you like. Have a good night.